Hello, everyone. On the second day of this awesome conference, we are brave people. We will write GC, custom GC, so it's very advanced and very funny and very interesting topic. So welcome to the talk about writing custom GC. My name is Konrad Kokosa, and maybe this is enough for you. I'm not. The most interesting is the topic, not me. So let's just kick off. So in general, welcome to the world of the custom GC in .NET, which unfortunately in .NET does not exist so much. I mean, there is no custom GC in .NET so far. It's quite opposite to the world of JVM. Is someone from you using Java for money? Perfect. Almost no one. No. In general, when we are using JVM, you are used to very different GCs available. Out of the box, there are many custom GCs that you can use. They were introduced from version to version. And moreover, each of those GC provides some kind of even further customization, a lot of parameters that you can use to tune how this GC is working. And of course, also people are used to the custom, let's say commercial one GCs, which they can plug in to the runtime. So people from Java world, they are just very used to the fact that there are very different GCs available. And moreover, all those parameters provide possibility to tune GC for their needs. So there is a lot of magic parameters that they can use to make it faster for their specific needs. Unfortunately, when Java people are seeking for solution, of course they are finding this solution on Stack Overflow. So they are just copy-pasting such set of parameters to theoretically tune their GC to their needs, but making use of less or more complicated list of parameters. But for me, this is kind of a disadvantage because in reality, no one really knows what those parameters mean, and no one really cares. I mean, people are just copy-pasting those solutions, making hope that it will help. But it is, for me, something which resembles cargo cult programming. I'm not aware if you are aware of the term cargo cult programming. If no, seek for it in internet. It's a very funny story, but for me it reminds me cargo cult. I will name it cargo cult configuring. So it's a way of making something in the hope that it will work. Some magic happens and it should work. And it's exactly like that with a lot of those parameters. So .NET by design chose a completely different approach, and it is an advantage. It is from the very beginning designed that way that they do not expose so many parameters, but they just provide very high level way of configuring GC. And this is by design, and Maoni pointed to me precisely that it is advantage of .NET, not disadvantage. Maoni, which is a main designer and the maintainer of GC in .NET. So, but why at all we should think about different custom GCs? In fact, this is because if something is for everything, it most probably is not good at anything. And making a very generic solution, which is a GC in .NET runtime, which should be good for anything that you can imagine, is really hard to implement, because somehow this GC should adapt to our needs. And obviously we are thinking about very different workloads in our applications, very different expectations how our applications should be used, how the GC should behave, how memory management should behave. And when talking about GC, we will be then looking at it from the very different perspectives. We can think about whether GC introduces big memory overhead or no, whether it introduces big CPU overhead, what are the pauses, whether the most important is latency or maybe throughput. There is a very different number of things that can be important for us when looking about how GC is working. And obviously making a very generic GC which is good at all of these aspects is simply not possible. So .NET took this very high-level way of configuring GCs, which provides very simple high-level configuration, let's say knobs, toggles, and modes to configure what is important for us. Obviously, I hope most of you are aware of those which are GC modes. So instead of those many magical commands, you have simply kind of currently 4 possible modes you can use in your application, whether it's workstation and server, and whether it is concurrent or non-concurrent. And so the obvious is here very limited. In fact, only those 2 are the default ones, so most often you will just use these 2. And this is a very simple, let's say, decision for us, because we have only 2 default, most probably working good working GCs in our applications. So this is as a kind of introduction how it looks like now. From the perspective of the current implementation, server GC, just to note how it is implemented today, to see how we will implement it. All those 4 modes of GC, current GC, are implemented in a single file, which is named GC CPP. This is very funny, really, to analyze this file, because it has only 40,000 lines of code, so it's very simple to understand. Moreover, those 2 types of the GC, whether this is a server GC or workstation GC, is defined by the precompiler constants. So when we analyze this file, we have in mind we should think whether we are now in the context of server GC or workstation GC. So this is kind of mind-blowing to understand what is going on. For example, even parameters are conditionals around conditionals. So some methods are taking some arguments in server GC, some are not. So this is really fun to understand this file. It is really huge, and people are asking whether .NET is planning to refactor this, but the approach is that it is working, so we should not touch it simply. So they probably will never refactor this file. From the perspective of whether this is concurrent or not, things are a little simple, because the constant defining the concurrent GC is always enabled, so at least we always know that all runtimes support this, but still there are dynamically checked flags whether we are running in concurrent or non-concurrent version of GC. So again, the complexity is again more bigger and bigger, because now we have to think not only about server, not non-server, but also concurrent and non-concurrent. So this is how they did it, and this is now we can completely get rid of it in a topic of our talk when writing our custom GC. So this is the approach they took. Obviously, through the times of the .NET existence, there are some additional configurations that they added to tune .NET a little, the GC a little. So maybe you are aware of those configurations, like limiting the number of heaps in limiting the number of managed heaps. You can configure latency modes, which will be soon replaced by something that they call latency optimization goals. But still, all those are very little tuning around some aspects how our current GC is working. But we can't in any way change how the GC is implemented. We can go a little bit further to use CLR hosting to tune memory management a little. CLR hosting is a possibility to host your own runtime inside native process. So this is, for example, the most known use case is SQL Server, which is hosting CLR inside to make running managed code possible. So this is a very known use case of such CLR hosting, but we can use it for our own purposes. We can host CLR in our process because it allows us to override a set of interfaces that this CLR hosting exposes. There are many more. This slide present only the one related somehow with memory management. So we can see that we have a lot of some methods we can use, for example, to collect statistics and so on. But from our perspective, the most important ones here are related to listed here. So we can somehow override how runtime consumes memory from the operating system. In other words, we can override such crucial methods like virtual allog or virtual free. So every time runtime will ask operating system for the memory, it will go through our custom implementation. So instead of using typical virtual API from Windows, we can use anything we want, taking memory from, I don't know, disk, network, Cosmos, no, I don't know, from somewhere. We can just override the way how the runtime sees memory from the operating system. So this allows us only to customize this little layer between runtime and operating system, but nothing more. So from the GC perspective, it is completely not usable for us, but still we can tune it a little. For example, this is a very simple example how you can create such CLR host. I will not explain it here, but because it's not the topic of this talk, but you can then look at this slide and just see and try by yourself. So by hosting, we can plug some interfaces and use some custom methods. One of the methods which allows us to tune a little the GC is this one, which allows to set startup limits for the segment size, for example, what are the default segment sizes, but still it's very limited. What we can do more is, for example, override those interfaces implementing virtual allog, so we can create our custom memory manager. And one of the practical examples of such approach is to tune a little how virtual API is used, because we can just use virtual API as usually, but we can add virtual log to log all memory which is gathered from the operating system. By logging, I mean this memory will always stay in physical memory, so it will be never swapped to disk. So this is a kind of creating a host which makes runtime and its all memory always staying in physical memory. So it's a kind of non-paging CLR host. You can look at the full working example of such host on, I don't know how long this address will exist, but until Codeplex will be shut down completely. But there is such implementation you can look and just and even use and play with it. But from perspective of customization of the GC, obviously all those possibilities are very not interesting. In fact, doesn't allow to do anything with the GC itself. And it was a situation until .NET Core 2.0 when the project called Local GC was introduced. You can also know it as custom GC or standalone GC. In fact, the idea is very simple. They go completely on the second approach. Instead of exposing a lot of parameters to be tuned, you can just completely replace GC, so implement your own. Very simple stuff, you know, just to implement your own custom GC. You can track the progress around this project on GitHub, because it's obviously only currently in Core CLR. It's public on GitHub, so you can track. There is a dedicated project on GitHub for it. What's interesting that this is not completely finished. So although it is completely usable in the production-ready .NET Runtime 2.1, there are some still items in backlog to be implemented, mainly around diagnostics. But it is usable, but not yet finished. mainly because most of those tasks were assigned to the guy which is not working in Microsoft anymore. So maybe this is the status of the project is a little bit frozen. So, but luckily he has finished this project before leaving, so we can use it now. So what can be done with this local GC? We can say that everything, in fact, because we have completely blank page about which we can fill with our custom GC. Well, almost everything can be done because there is a kind of coupling between the runtime and the GC, and we will see it that sometimes it limits us a little what can be done. From the perspective of the usage, is very, very simple. They done it in a very nice way. To use custom GC, you have to do two only things. Implement custom GC, the easy one, and the second one, set environment variable, which provides a full path to library implementing your custom GC. And when the runtime is initializing, it will notice such variable, and it will initialize, and it will load GC from this file instead of loading it from itself. So it is very easy usage. In case of .NET Core 2.0, it was a little bit more complicated because then this project was in local, it was in preview mode, so we had to recompile runtime to make it enabled, but from the 2.1 it is enabled by default. And what's important here when you will be playing around with custom GC maybe, you should remember that this variable is wide for all .NET processes in the context of the shell of the system which is seeing this variable. So for example, if you set this variable in command line and then we will type .NET build, .NET build itself is a managed process, so it will also use our custom GC. So we should be aware of this, especially in our zero GC, which is not freeing memory, so compiling big solution can just blow your memory completely because .NET compiler will use our zero GC, which is not very fortunate. So you should be aware that it is for all processes which are seeing this variable. Okay, so this is a usage, and what about implementing it? Implementing is also, we can say, easy. We are just implementing a kind of a regular C++ library, so we can use Visual Studio. The coupling was done very nicely, so we have to only include 3 header files from core CLR source. We need to have core CLR cloned on our disk to include those 3 files, but they are only 3. And then we have to implement 2 methods, kind of meta methods, which provides information about our custom GC, and then obviously we have to implement the rest of the GC. By implementing those 3 very crucial interfaces, IGC heap is responsible for everything related to the GC because it's the implementation of the managed heap. Then we have IGC handle manager and handle store responsible for handling handles. So because handles are a very important concept in the runtime itself, they are used through the runtime for many purposes, and we have to implement some kind of handling handles because it's required. So for me, it reminds me a kind of this funny picture because we have to include few files and then only implement the rest of the GC. So it's easy, yeah. But seriously, is it difficult? From my perspective, I could say that it's not very difficult, but it requires some knowledge about the runtime itself and also about the GC itself, which can be kind surprising because we are writing our own. But the coupling, there is a coupling between those concepts, so still we need to know something about internals of both the runtime and the GC. Yeah, as you will see, you will have a chance to see whether it is hard or not. So how we could implement it? The very first method that you should implement is this GC version info. It provides information about what GC API version we are supporting because they introduced concept of the GC API version. because obviously this API could be changed in the future. So there are different versions of the GC API. Currently there are only 2 versions, but still we have to say what version our library supports. And runtime, when it's loading this library, is checking whether it is compatible with this API. Strangely enough, currently it only works for me if I swap minor and major version. I don't know why, but believe me, it's like that. I created issue on the GitHub saying that it is a bug, but it was shortly closed saying that no, it is not a bug. So it's open issue whether it is my fault or their, but still currently when you're looking into the code on GitHub, don't be surprised that I change the minor and major versions. So still, this is very easy method. Then we have to provide method which provides information about custom implementations. This method should return pointers to the custom implementations of the GC heap and handle manager and handle manager. So we are just setting those pointers to our custom ones classes, implementing those interfaces. And secondly, very important thing, we should remember pointer to the interface exposed by the runtime to the GC for various purposes. So we are getting here from the runtime address of the interface, providing very important API, for example, for suspending all threads and restarting all threads, because we will probably need this in implementation of our GC. And very important method for scanning roots of methods, because we will at some time need to scan what variables are there, what are the roots. So those are the methods exposed by this API, and we will use this, we may use this in our implementation. What about the IGC heap? It's very simple. It has only 75 methods, so implementing it is very, very fun. I mean, obviously we have to remember this interface, and then we can look about all those methods to be implemented, which is looking a little bit scary because there are 75 methods, so it looks like a huge of work. But what in fact must be implemented to make it working? When we look about this cooperation between the runtime and the GC, there are a lot of methods which are highly coupled with the current implementation. So we will see a lot of methods like set GC latency mode or set large object heap compaction modes, which are completely useless in our custom GC because we probably won't have a concept of latency or large object heap. So a lot of those methods is coupled with the fact how currently GC is working, how finalization is working, and so on and so on. So in fact, we can, when implementing our custom GC, especially very simple one, most of these methods can be somehow omitted because they are not important from the perspective of our very simple implementation of the GC, which is good for us. At least we don't have to think about all those 75 methods in case of, in terms of complex implementation. So when I saw this project, I thought it would be nice to write kind of very minimal valuable or viable product to see how I could implement GC, which is doing nothing. But it's very good base to write something more complex, so we have to start from something. The zero GC is a concept now in literature, so it is a concept of the GC which is only allocating and has no garbage collection at all, because one of the most important responsibilities of the GC is to allocate objects. So obviously this we have to implement, but then we are just not making any garbage collection. So as I said, in case of such a zero GC, most of the methods is simply dummy, returning some very simple data without any calculations, because we have no generations. The method is promoted, doesn't make sense for us, and it will be not even called because it is how the finalizing is currently working, and this is called by finalization. And and there are a lot of like that methods. So get condemned generation returns 0 because we have no generations, so there is no sense in answering this question. So a lot of these methods will be like that. Then we will have this method, which looks quite seriously. I mean, it's garbage collect, so it looks like it is a one which is making garbage collection. But in fact, it is not true. It is a method called by the runtime occasionally in the scenarios when the runtime is asking GC, is triggering GC. In case, for example, of GC collect call or so-called low memory notification sent by the operating system, which triggers GC explicitly. But this is not called by the in the very typical scenario of allocating objects. It is a, let's say, external call to trigger GC. So our implementation will be very simple. And here, in the default, the current GC, this method is starting the normal GC. We are just doing nothing. So this is, we get rid of garbage collector. And this is those allocations which are the most important ones. The typical path in each garbage collector is that it returns an object, an address to a newly created object, but also there is a possibility that those allocation will trigger a new GC. And it is a very common path of triggering GC in our applications. We are allocating objects, and now at some time a GC notices that it is running out of memory in some context, and it is triggering GC to free some memory. So it is implemented in default GC, and in our case, obviously, we will get rid of this triggering. So because we have only 0 GC, so we will not trigger any GC because we don't have any, and we will just return an address for an object of a given size. And this, the very first implementation was just to call calloc, which returns a native memory from the operating system with a given size. Two very important notes here. First, that I have to use calloc, not malloc, because calloc is zeroing memory, and zeroing memory is a very crucial requirement from the GC, because this is why references are nulls, integers are zeros. So if you would not zero memory here, the very strange things could happen. So we have to zero all this memory. And we have also to create a little bit more space, because this method is creating a space for the whole object, including header. So the runtime is asking me for some kind of memory, for memory of a given size, because of the method table pointer and the fields. But I have also implement giving a space for object header. So that's why this a little bit strange address +1 is happening here, because I'm returning an address inside this newly acquired memory, just to have a space for an object header. If I would be returning only the very beginning of this memory, at some time probably access violation would happen, because the runtime would like to write memory before the method table, which would be outside of the allocated space. So I have to provide this a little bit space for an object header, and that's why I'm returning this size of memory. And yes, this is this is simply working allocator that obviously is very inefficient, because we are just for each and every object allocated, we are just asking operating system to allocate some memory and zero it, and so it's a very big overhead. But it's working. I was very surprised even that it just worked. Then we have those handles. Handles are very important because there are pinning handles, strong handles, and things like statics, local thread statics, and many other strings interning depends on handles. So we have to implement handles to make the runtime working. And my implementation is trivial. I just create a table with a fixed size for all the handles. So at some time, obviously, I will hit this limit, but this array is big enough for my scenarios to make it working. Just to, I was in a hurry just to see if it will be working. So I would obviously, in the future, I will replace this with kind of dynamically growing array. But for now, it is working. The handling handles is very easy. I just provide a slot from a constant array of handles, and then when the runtime wants to store handle in the handle table, I'm just writing an address under a given address. So the implementation of handles here is trivial. And that's almost all when we want to implement such a very simple calloc-based GC. You can look at this repository, you can even compile it and run on your production environment, obviously. I said mostly, because there is a little caveat here called write barriers. And this is one of the moments when we need to know runtime a little to make it working, because in the current one implementation, it will just unfortunately crash the whole runtime because of this. Card tables, I'm not sure if you are aware of this concept, is it is an implementation of the more general concept of remembered sets, which is a way of handling cross-generational references. Because we want, for example, to garbage collect only generation 0 in the default GC. So we are just visiting objects in generation 0, but there are some objects which are living because they are kept by all objects from older generations. And then we have to have some kind of tracking those references from older generations to the younger generations, and those are maintained by those card tables. Every time when you assign a reference between objects, it goes through so-called write barrier, which writes this reference obviously inside those inside this object, in this target object, but then it also updates card table to remember that under this region there is an object in an older generation that references younger one. So then when marking the living objects, we are also starting from all those card tables when potentially there are objects referencing younger objects from older generations. And this is implemented in write barrier, and this is a very first slide with assembler on this conference. I'm very happy that I can introduce assembler here. This is a write barrier from core CLR. This is a code which is injected by JIT for every single reference assignment in your code. Every time when you assign object to an object field, this goes through this method. Obviously, the very first one is the most important, which makes those assignment by itself. But then, as you see, there is a code responsible for updating this card table. And obviously, it will crash because we don't have card tables. We don't want to have card tables. It doesn't make sense to implement card tables just because of this code. So we can make use of those checks, because this write barrier is checking whether the target object lives in the younger generation. And it makes those update of card table only if it is indeed living in the younger generation. So those two checks we can use, because we are checking here boundaries of so-called ephemeral region. So the region holding the generation 0 and 1, the younger ones. And by fooling runtime, providing artificial boundaries of this region, we can make this write barrier always working. I mean, this is kind of fooling and magic and hacking, that we provide impossible addresses of the ephemeral region. So this check will always fail, and we will always omit the label updating card table. When by this we are just making it, we are fooling runtime about the fact that the card table should not be updated. So this is quite a very high coupling between the runtime and the GC, which we have to be aware of to properly implement our zero GC. It's quite, unfortunately, not very luckily way of implementing those write barriers, but as they said, they probably will stay with it. There is no plans to implement a way of let's say injecting our own write barriers. So we will have to live with it. And moreover, it is very interesting because it is a kind of paradox that we have to use workstation GC mode in our custom GC, which has no concept of workstation and server, but still runtime has this concept. And this write barrier is injected only in case of workstation GC, and in case of server GC there is another one write barrier which just is not checking these boundaries, so will crash always, unfortunately. So this is a kind of paradox that you should remember to set workstation GC when implementing our custom GC. Still, it is working after this fix. We can just create very simple web API. We can make very simple controller which returns something. We can build it, set the variable, and run it. And the results were quite surprising because, as you may see here, the default 1.0 GC was able to get the throughput at the level of 700 requests per second. And our very poor man's implementation of the zero GC was also able to get throughput at the level of 700 requests per second. So it's quite nice because it's the same level of the performance we have as with the default GC. This is because this load test that I'm doing here, load testing this web API, is a little bit contrived. I mean, this is very lightweight controller with a very low number of GCs being triggered, and the number of allocations also is not so very big. So this benchmark is not very good, and I'm looking for a better one. But still, at least I was very happy because I was able to load test my custom GC. It was able to process 24,000 of requests without crashing. So this is a kind of success. Looking at the result from the memory usage perspective, this is the default one, obviously. The memory usage is constant at the level of 24 megabytes. And this is, guess what, mine implementation, which is obviously not releasing any memory. So after those 24,000 of requests, after 1.5 minutes, the memory usage was about 300 megabytes, which is still quite usable. I mean, for very short living processes, maybe it is worth to just not trigger GC at all and just kill this process. Okay, so what's next? Obviously, I was not very happy about this calloc-based implementation because it is by default so slow, and I wanted to implement so-called bump pointer allocator, which is a very typical way of implementing allocators in managed runtimes, which is based on bumping allocation pointers. So we have some memory region within which we are allocating objects, and when we want to allocate an object, we just bumping this allocation pointer, and we have just received a memory region for our object A. So this is very simple implementation, and it can be very fast because, in fact, it's only operating on a single pointer, checking whether it is okay and checking and adding size to this allocation pointer. In this context, most usually we are talking about allocation context, which is a pre-zeroed memory region within which we are allocating. Obviously, it has some limit, so we are bumping pointer until we hit this limit, and then we are looking for a new allocation object, allocation context. Sorry. So this is how allocation contexts are working, and this is exactly how current default GC is working. So it's based on allocation contexts. We have this very fast path in which we are just bumping this pointer, and then we have slow path in which we are looking for a new allocation context. This is how GC is working. This is how it looks like in the current implementation in the .NET itself. So there are many allocation contexts because each managed thread has its own allocation context. So there will be so many allocation contexts as managed threads. This is very good from the implementation perspective because we don't have to care about thread safety. Only single thread is only accessing the single allocation context. And this is important from our implementation because there is a thread affinity ensured by the runtime about this allocation context structure. There is only one allocation context structure per each thread. And if we look at this alloc method, which we were seeing before, there is an argument called GC alloc context, and it is exactly that. This is a structure managed for each managed thread separately. So each managed thread will have this, will have another structure here, another address. And this structure contains important for us pointers, allocation pointer, and allocation limit. This is because, as I said, current .NET uses allocation contexts, and we can reuse those pointers here in our custom implementation of BAM pointer. So the fast path will be very easy to implement because we have simply implement this bumping pointer, checking whether we are still within the limit or not. And the slow path is again very trivial. I decided to use simply virtual alloc to allocate pre-zeroed segment of 16 megabytes. It was the simplest thing that I could think of. So I'm just getting from the system allocation context of the size of the 16 megabytes. And obviously, it is by default pre-zeroed because it is a guarantee given from the virtual alloc. So we have pre-zeroed 16 megabytes. And we are returning allocation pointer from within this newly created region. There is still one thing we should remember: those object headers. So we can't return just the very beginning of such single segment, because still runtime would like to read our write object header from the very first object, which will be outside of such segment because it will be before the first byte. So we have to create a little gap for the object header for the very first object. And now, after all those fixes, again, I was quite surprised, but it worked. So this is a very simple implementation of such bump pointer allocation. And as you see, there is alloc method, and there is also alloc L heap, which allocates objects on large object heap, but only in case when runtime wants to allocate their objects which are smaller than the default threshold for objects in large object heap. There are some rare cases when it wants to allocate explicitly something in large object heap, even if it would not be there. And those are mainly hand tables. And so this is a so rare case that I just wanted to ignore this, because there are only few such tables created, so it was not worth, especially that this method is not thread safe, so I would need to implement my old thread safety here. So for now I just ignore it. And then we are hitting another one caveat, that allocation contexts are reused by the runtime itself and by the JIT. It is another point in which we are hitting this very high coupling between the runtime and the GC. Because if we look at the decision path of the JIT, when the JIT is seeing a new object IL instruction, it makes the decision which method it should inject. And for methods which, for objects that are large, or for objects that has finalizer, it is using so-called JIT new method, which eventually falls back to our custom allocator. But for other method for other objects. So let's say for most objects, in our applications, because most objects in our applications are smaller and doesn't have finalizer. So for 90 or 90% of objects, it took this write path in which it injects assembly code directly without hitting our custom allocator at all. Depending on the platform and whether the allocation contexts are used or not, but most typically this decision lands in this JIT trial alloc as fast npm inline get thread method. Very simple name. So a lot of allocations doesn't go through our custom allocation, in fact, but through this JIT inlined code, which looks like that. And it simply implements bump pointer allocation, but in assembler to make it extremely fast. So for 90% or 80% of objects allocated in the runtime, by the runtime, the allocation happens through this assembler. So this is only checking those allocation pattern limit and returning the address. It is extremely fast. And for us, obviously, it is quite surprising, but because now even that we wrote our own custom allocator, most of the allocations still go through this one method. Obviously, it will be working because here this code is reusing those allocation pointer and allocation limit pointers that we are setting in our custom allocation. So as you see, for the it is reused, so it will operate on this created by us memory segment, and when this allocation will hit its limit, it will fall back to this JIT new method, which is seen at the very end of this method, and this JIT new method will eventually fall back to our custom allocator. So this is working. Just because we are setting those allocation limit and pointer properly. But we should be aware that most of the allocations will not happen through our custom allocator, in fact. So obviously one could ask why calloc was working, if it was working but not using this. This is of course that because in the calloc-based version we didn't set allocation pointer and limit. Those comparison was always failing, and this allocator was called, but then always falling back to this JIT new method. So our calloc-based allocation is very inefficient because it is always going through this path, and then the JIT new is being called, and the JIT new calls allocate object, and allocate objects eventually calls our custom allocator. So this is the path that we should be aware of, that we are just going this quite strange path to eventually hit our custom allocator. But still it is working, so it is nice. But in our bump pointer implementation, it works because we have this pointer set properly, we have set limit properly, so it is just working, and we are reusing this JIT coded allocator, which is nice because we gain a full speed of the allocation in fact. Obviously, one could think that it is not very good, and you would not reuse this, JIT code, and by not using those allocation pointer and limit. And for that scenario, we could just use another pointers, two GC reserved ones, pointers for a generic purpose of the GC. So we could think about not using allocation pointer and allocation limit here, but create our own bump pointer implementation using those two fields. So then we will manage the allocation pointer and limit with the help of those two fields, not by the help of those two fields, but which are used by default. So it's a kind of omitting this problem. But still, as you see, we have to really know deeply the internals of the runtime to write it properly. And the results are very similar. it's now 600 requests per second, not 7. I'm not sure why. I'm not happy with that. It's slower than Calloc. But this is all work in progress, and I hope I will find out the reason. Maybe it's also because the way of testing this is very contrived, so I believe I'm just waiting for a better benchmark. But still, it has worked. So again, victory. And from the perspective of memory usage, it is a little bit smaller even. I mean, then in the Calloc-based scenario, we were hitting 300 megabytes. Now we are hitting 200 megabytes. Because Calloc is a not very efficient way of implementing allocations. It introduces some fragmentation. We had overhead of object header per each object. Now we are managing memory in segments, 16 megabyte segments, which makes this more efficient. So we are just reusing less memory in such case, but still, of course, it is leaking because we don't do any collection. But still, it works. And if we would like to go further, because here we will just stop, not implementing the next iterations, but when implementing the GC, and the more sophisticated one, we have those kind of infrastructural support from the runtime. For example, we can emit events, ETW events or LLTNG events in case of Linux. The well-known for events like GC start, GC end, and so on, or we can generate our custom one. We can also use those methods from EG from the interface provided by the runtime for the thread suspension, thread restarting, for creating threads, because we might need to create threads in our custom implementation of GC. So we all have here this available, and methods for getting configuration from configuration file. Our runtime also provides these methods. So we all have here that, and we just need to implement the rest of the GC. So what's next? Obviously, we have to draw the, and one could now ask why we should even care about all of this. I mean, for me, and hopefully even for you, I invite you to contribute. It's a lot of, I've learned a lot about the GC and the runtime cooperation, making all this. It's a great fun to see that you can completely replace this unfortunate 40,000 line of codes by 3 line of codes that it is working. And obviously it opens the door for a world of JVM when we can create specialized, even commercial GCs for specific use cases. For example, one of you may write the very long-awaited concurrent compacting GC because of that, which is obviously not so simple. Or even this zero GC. I see practical usages, but because maybe I'm a little not objective here because I wrote it. What about finalizers, one could ask. Currently, I obviously just ignore it because there is no collection, so there is no concept of finalization. Runtime still creates finalization treat, so in general, there is a finalization concept in the runtime itself, but as far as I know, there is no API how we could communicate with this. So this is completely not known area for me now, whether we should implement our own finalization or whether there is a way to reuse this one used by the runtime. So this is something that should be investigated. And also one could ask, what about such things like multiple heaps in case of server GC, multiple GC threads in case of server GC. As I said, this is completely on the side of the GC. So obviously, when we want to implement something like that, we just need to implement creating GC trees, creating multiple heaps, and so on and so on. So this is really quite complicated, especially if you want to do things like .NET currently does, like heap affinity between managed thread and core to make it faster, and so on and so on. So it is not trivial. Okay, we have a little time left, so let's just let you with some literature. If you would like to implement GC, there is no better source than the first one book. It is a Bible of GC, every possible GC ever created is described there. So just open a page on a random page and implement the GC described there. Then there is a mine book, which is a little suggestion from me. It is good to, because it is good to understand how it is currently working, to implement your own way of doing this. So there is this book, and there is those 2 blog posts in which I describe simply what I've just described. My name is Konrad Kokosa. I invite you to follow me on Twitter especially. I'm gathering followers. It's my hobby. Usually I don't do such marketing stuff, but currently there is a very nice promotion on Appress. You can get every ebook for even only $7, not only mine, but every ebook. So it is a really great time to buy a book. Sorry, and that's all. Thank you very much, and maybe we have some time for question.
Well, we have one
minute.
Question, yeah.
Okay.
Thank you so much. Applause, please. Поднимите руку, у кого есть вопрос, я подойду с микрофоном, и вас будет слышно хорошо. Да, окей, вижу. У нас в дискуссионной зоне через пару минут окажется спикер, поэтому все, кто не успел задать вопросы, могут задать их там.
Hi, thank you for your speech. You told us about that in 90% of cases, the memory allocation happens in the code generated by JIT, right?
Yes.
And what problems does it potentially bring us?
In general, it doesn't bring any problem until we implement our custom GC. So we should be aware of this path, that it is using those allocation pointer, limit, and pointer. So you have to set it to make use of this JIT code, or just ignore it and be only aware that other allocation will still go through it. So you have this performance hit of going through this code even if you are not using it. And this is the main problem. And unfortunately, from my perspective, it would be ideal to expose some kind of API to just set the code which is injected by JIT in this case, but I don't expect it will ever happen, unfortunately.